Welcome, everyone, to another Explainer. Today, we are taking a grand, evidence-based tour of our home and looking at exactly what it takes to protect it. I'm super excited to guide you through this because we're going to look at everything from the very foundation right beneath our feet to the invisible shield up above our heads and all the intricate, beautiful balances that keep us alive.
All right, let's just dive right in with a simple but honestly profound fact that sets the stage for everything else. Earth is the third planet from the Sun, sitting at an average distance of about 150 million kilometers. But the most crucial part of this fact is that second half. It's the only astronomical object we currently know of that harbors life. Everything we're about to discuss today revolves around the wild physical systems that make that extraordinary reality possible.
We have got some fascinating ground to cover today. We'll explore 1. Inside our ocean world. 2. The atmosphere and biosphere. 3. The greenhouse climate disruption. 4. The downsides and feedbacks of those impacts. And 5. How to actually stop global warming. Okay, Section 1. Inside our ocean world. Let's look at the foundational, physical properties of our planet. So look at this. This perfectly illustrates why we call Earth an ocean world. Nearly 71% of its surface is covered by liquid water. That leaves just over 29% as land, which is where we build all our cities and grow all our food. That vast pool of salty water is what makes our dynamic hydrosphere possible. And get this, among all the rocky objects in our solar system, Earth is literally the only one sustaining liquid surface water, which is the absolute prerequisite for life as we know it. Now think about what's right beneath your feet. It's a pretty intense internal structure. We live on the crust, which is astonishingly thin. It's only up to about 35 kilometers deep on land and even thinner under the oceans. But as you travel downward, gravity has pulled the heaviest elements toward the center. By the time you reach the inner core, over 5,000 kilometers down, you've got a solid ball composed mostly of iron and nickel under immense pressure. And the temperature down there? It reaches 6,000 degrees Celsius, which is roughly as hot as the surface of the sun. That massive internal heat is exactly what drives the tectonic plates on the surface, pushing up the very mountains and continents we live on. Moving upwards from the core and the crust, let's examine Section 2, the atmosphere and biosphere. This is our invisible shield. Okay, let's look up. Nitrogen and oxygen completely dominate our air, making up about 99% of the dry atmosphere, with argon taking up almost another 1%. But the true focus here really belongs to that tiny 0.1% of trace gases. See, because oxygen and nitrogen molecules contain two atoms of the same element, they're mostly unaffected by thermal radiation. Heat just passes right through them. But those trace gases, like carbon dioxide, methane, and nitrous oxide, have an asymmetry that allows them to interact with electromagnetic radiation. That tiny fraction of the atmosphere holds massive, massive climate power. To put that power into perspective, check out this stark comparison. It shows how the natural greenhouse effect traps thermal energy and literally makes our current form of life possible. Without those trace greenhouse gases absorbing and re-radiating heat, our planet's average temperature would be a freezing -18 degrees Celsius. But thanks to this natural atmospheric shield, we enjoy a super comfortable, life-sustaining global average of +15 degrees Celsius. It's a perfect, delicate balance that has been relatively stable for the past million years. But what happens when we mess with that balance? Let's transition to Section 3, the greenhouse climate disruption. This number right here represents the totally unprecedented rate of human-induced warming we've experienced lately. Between 2015 and 2024, the global average temperature rose at a rate of 0.27 degrees Celsius per decade. Now that might sound small to you and me, but in planetary terms, that is a staggering acceleration. This is being driven by greenhouse gas emissions hitting an all-time high of over 53 gigatons per year. That is a frankly unimaginable mass of invisible gas. By digging up and burning fossil fuels like coal, oil, and natural gas, we are rapidly thickening that trace gas layer, trapping way more heat than the natural system was ever built to handle. To understand the physics behind this warming, scientists look at a metric called radiative forcing. Basically, positive radiative forcing from all those extra greenhouse gases means more solar energy is arriving and staying here than is leaving back out into space. It fundamentally shifts Earth's energy balance. And just like a heavy blanket trapping your body heat at night, this positive forcing warms the lower atmosphere and the surface, which inevitably scrambles our global climate systems. So, what does this look like on the ground? Let's check out Section 4, impacts, downsides, and feedbacks. The sources detail a pretty overwhelming list of global consequences that threaten ecosystems and our own food security. Because the oceans absorb much of this excess heat, we're seeing intense thermal stress, causing mass coral bleaching events. We're getting slammed by extreme weather, where altered atmospheric patterns amplify both devastating droughts and catastrophic floods. Up in the Arctic, disappearing sea ice destroys vital habitats, while thawing permafrost poses this huge risk of releasing trapped methane, which is an even more potent greenhouse gas. On top of that, as oceans absorb the excess carbon dioxide, they're becoming more acidic, expanding dead zones where marine life simply cannot survive.
Now, looking at this impartially, the science also shows some highly complex biological responses and feedback loops. Sometimes these are labeled as localized upsides or synergies. For example, higher levels of CO2 can actually have a fertilizing effect on certain types of plant growth. There are also potential localized synergies, where a warmer climate might briefly bump up agricultural productivity in specific regions. But, and this is crucial, these same shifts come with dire biological feedbacks. Milder winters mean devastating pests, like the pine beetle, can survive year-round and kill off massive swaths of forest. Overall, while the system's response is incredibly complex, the data clearly shows that these localized effects are heavily outweighed by the negative global disruptions. So now that we understand the stakes, how do we fix it? Section 5. How to stop global warming. To keep global warming under the internationally recognized 2 degrees Celsius threshold, the data states global emissions absolutely must reach net zero by the year 2070. Reaching net zero just means we aren't adding any more greenhouse gases into the atmosphere than we're actively removing. Achieving this timeline is going to require far-reaching, systemic changes on an unprecedented scale across our energy, land use, transport, and industry sectors. The sources outline a pretty clear step-by-step framework to halt greenhouse gas accumulation. First, we have to aggressively phase out fossil fuels. A key part of this is stopping financial subsidies for them and transitioning global transportation and industry over to cleanly generated electricity. Second, we must rapidly scale up our deployment of renewable energy, specifically wind, solar, and hydropower, which give us energy without the carbon pollution. And third, we can't just stop emitting. We actually have to protect existing ecosystems and actively remove carbon from the air through large-scale reforestation and better soil management. And nature-based solutions are incredibly powerful for that last step. Just look at this data point. Tropical forest trees are literally absorbing about 18% of the carbon dioxide we add to the atmosphere from burning fossil fuels every single year. Trees in tropical climates grow year-round, making them massive carbon sinks. Restoring and protecting robust ecosystems like these forests is a colossal natural tool for carbon sequestration. It's this perfect synergy where we mitigate climate change while simultaneously protecting the biodiversity that supports our global food systems. I really hope this explainer has given you a clearer, more structured view of the planet we call home. From the dense, superheated iron in Earth's core, all the way up to those fragile, life-giving trace gases in our atmosphere, everything is connected. And by understanding the data and exactly how our world operates, we are so much better equipped to protect it. So it leaves you wondering, with this knowledge in hand, what role will you play in shaping the future of our one and only ocean world? Thank you so much for exploring this with me today. Keep asking great questions, and I'll catch you in the next explainer.